Thanks for the introduction, and I'm Donghyun Kim. And in this talk, I'm going to present a novel recommendation model to consider ratings and document context information. So let's start. As you already know, a popular matrix factorization is a popular model-based collaborative filtering technique for recommendation to generate user and item-latent models. And these item-latent models are used to predict unknown ratings, and it can be regarded as matrix comparison problem. So like this. And with these predicted ratings, we can recommend proper items to each user. But interestingly, according to the mention of Coran's previous work, these latent models can be plotted to two-dimensional space, and we expect that these user and items are placed on a proper position to two-dimensional space. But however, when the rating matrix becomes extremely sparse, user and item latent models will not be well trained, and it results in inaccurate position of users and items on two-dimensional space. And these inaccurate item user latent models cannot give good or better and best recommendation for each user. So to handle this sparsity problem, many authors have found the benefit to matrix factorization, incorporating matrix factorization with textual information such as review, synopsis, abstract, etc. And these are actual descriptions of many items, and as a research trial to understand description document for recommendation, collaborative topic modeling was introduced 2011 KDD by using LDA, and inspired by previous work, collaborative deep learning was introduced KDD 2015 by using stack denoising autoencoder. But however, they still use backwards models of item description to generate item latent models. So here is the question, are they enough to analyze description documents? And in other words, is it okay to ignore surrounding words of word and word order? The answer is no. In natural language processing area, considering surrounding words and word order as contextual information improves the accuracy of word vector in the word embedding, which was this result was published in NIF 2013 as word-to-vector model. So, what if recommender systems are able to capture or understand contextual information in documents? We can expect that more accurate item latent models will be generated through a deeper understanding of item descriptions. So, and this expectation is plausible based on the previous work, so the contextual information should be considered for better recommendation. So for those reasons, we develop a novel document context-aware recommendation model, convolutional matrix factorization. And it satisfies below three properties, and it is they are to consider contextual information and to effectively exploit both ratings and description documents, and to jointly optimize the recommendation model in order to properly predict ratings to items of users. Actually, ConvMF is inspired by convolutional neural network. For the natural language processing and IR tasks, many kinds of CNN have been actively developed to consider local contextual information in a document. Typically, CNN consists of convolutional layer and subsampling layer to extract meaningful local contextual information. So here is an example of CNN architecture for sentiment classification. And this model considers surrounding information for sentiment classification. So as our trial to generate more accurate item latent models for better recommendation, we use CNN and we model simple CNN architecture which consists of 4 different layers. And each layer has different purpose, and an embedding layer is to transform a raw description documents into a numeric document matrix by using word embedding models. And in this layer, we can use pre-trained word embedding models for better recommendation, and it is another advantage of CNN compared to LDA or SDAE. And above embedding layer, convolution layer is to extract contextual features from a document matrix by using multiple shared weights. For more detail, each contextual feature is extracted extracted by the similar way of sliding window to consider surrounding words or word order, and they compose contextual feature vector. And then pooling layer is to extract representative features from the convolutional layer while dealing with variable lengths of documents. And then finally, a document latent vector is obtained through nonlinear projection in output layer. But however, the existing CNNs cannot effectively predict unknown ratings to the same item for individual and different users. So to deal with this problem, we adopt the way of probabilistic matrix factorization, which was published in NIPS 2008. And in this work, ratings are probabilistically approximated by the variables of users and items. So with this probabilistic approach, we integrate CNN into PMF for the recommendation task to predict unknown ratings. So we model a simple probabilistic graphical model in here, and here is what variables are, and each variable follow Gaussian distribution. So among these variables, item variables plays an important role of the connection between PMF and CNN in order to exploit ratings and description documents. So with these distribution of variable, we can construct posteriori distribution, and to solve U and V and W variable, we use map estimation. So by taking negative logarithm to posteriori, we can obtain loss function here, and we use coordinate descent to update latent models U and V per iteration, because U and V can be solved analytically. And the interesting is that item latent models is updated by the summation of rating part and document part with balancing hyperparameter lambda V. And if the value of lambda V is high, the item latent model will be mainly updated by the document information. But W variable of CNN cannot be solved analytically as we can do for U and V, because CNN has multiple nonlinear properties. So, but however, fortunately, when U and V are temporally fixed, loss function L becomes an error function with regularized terms of neural network. So we can optimize W variable by using backpropagation algorithm with given target value Vj. So one iteration consists of U and V update and W update procedure. And then from now on, I will give our experiment and research. Here is our data set, and this table shows the statistic of our data set. And below two figure shows the sparseness and skewness of our data set. And as you can see here, AIV, Amazon data set, is the most skewed and sparse data set. And our baselines are here. And additionally, we compare CombMF with CombMF Plus to check the impact of pre-trained word embedding model. And we measure RMSE score, which is the convention measure in the recommender system. And this is our result. This table shows the rating prediction error of 5 models on each test data set. And improve indicates relative improvements of CombMF over the best competitor CDL. And especially in the case of extremely sparse data set, our models shows extremely significant improvements. So, and then also we can also see minor improvements by pre-trained word embedding model. Overall, CombMF and CombMF Plus achieve significant improvements on all the data sets. And we also investigate the best performing value of hyperparameter lambda U and lambda V. And as we've discussed before, higher value of lambda V implies that item latent models will mainly updated by document information, and lower value of lambda U implies that usual latent models will be mainly updated to the direction of latent space of item latent model. So this natural pattern demonstrates that CombMF is well modeled because extremely sparse data set requires a higher value of lambda V to use content information. And we also investigate the impact of pre-trained word embedding model. And as you can see here, the test error of CombMF Plus gets decreased as the dimension size of word embedding gets higher. So it is obvious because information contained in the word embedding model gets richer when the dimension size of word embedding model gets higher. So lastly, this qualitative experiment verifies whether CombMF is able to distinguish subtle contextual differences. So we compared contextual feature values of phrase, including word trust, captured by 2 different shared weights of CNN. So note that a higher feature value has more chance to affect the performance of CombMF. So the interesting is that when we replaced a word trust with believe face as semantically similar word but synthetically different word, the differences between that test phrase implies that weight variable W11 is more likely to capture trust as a verb, and W186 is more likely to capture trust as a noun. So this result implies that Conv MF can consider the same word differently with different context. So this result, this leads to a deeper understanding of documents and gives further improvements in recommendation. So in conclusion, we demonstrate that considering contextual information provides a deeper understanding of description documents, and we seamlessly integrate CNN into PMF. And since ConvMF is based on PMF, so ConvMF is able to be extended to combining other MF-based recommendation models such as SVD++. So this is the end of my presentation. Thank you for attention.
So thanks, Dong-Hyun, for the presentation. Are there questions? Oh, I have one question about the evaluation procedure you adopted. I see that you used error matrix in order to evaluate the quality. Did you also try accuracy matrix? Why did you choose error matrix in order to evaluate the results? Did you try also recall or precision or classification matrix?
Actually, this data set is explicit feedback data set. So I think that the better recommendation model to predict ratings is more. I think that it is more proper, more suitable to measure our model. So we can consider the other metric, but I think RMSE is the convention of the our area measure, so we use it. And
thanks. Are there other questions? Oh, yes, one there.
Can you say a few words about your setup? Did you use any libraries?
Oh, we use Keras library, and detailed experiment setting is in our paper. And actually, Keras is powerful framework to develop deep learning method.
Okay, so if there are no other questions, I would like to thank again our presenter.